welcome to another AQA AS chemistry video. I'm going to be doing a video on carbon structure and metallic bonding. So first we're going to start with carbon structure. So carbon structures, I'm going to first want to start off with diamond, which diamond is an allotrope, which is a form of carbon. Diamond has the following properties. So it has covalent bonds, covalent intramolecular bonds, where each carbon atom in diamond is bonded to 4 other carbon atoms by each carbon atom in diamond is bonded to 4 other carbon atoms by strong covalent bonds. So there's no delocalized electron. It can be described as being saturated because you can see here every carbon atom is bonded to 4 other carbon atoms, right? And you see, oh, this is probably a better example, right? There's no delocalized electrons because every carbon covalent bond that can possibly be formed is formed. So there's no space for another. And these carbons here that it looks like it's in diamond, they're free. They're not free. They'll form another. This is a 2D diagram, so you can't see it. But 3D wise, it'd form another bond with another carbon that's there, another carbon that's there, and another carbon that's down. So they're all 4 carbon covalent bonds are used up. So there's no delocalized electron, and it can be described as being saturated. And this will create a giant covalent structure with a high energy to break. High energy is required to break the fully bonded structure. So because carbon-carbon bonds are non-polar bonds, and there's many carbon-carbon covalent bonds, carbon-carbon covalent bonds, regular lattice, this ticks all the boxes for very, very strong compound that requires a lot of energy to break. Hence why it's the strongest material known to man. It requires a lot of energy to break. It requires the most energy to break any compound. So yeah, that's the. And realistically, all these the intermolecular force and or the type of bonding in itself determines the features really, and that's everything. When you're talking about the physical properties like hardness, solubility, all the things I'm going to talk about, all these like physical factors, they all relate to the type of bonding that you have. So the other feature of diamond is that it's hard, right? So there are lots of strong covalent bonds in diamond, making it very hard. As diamond is hard, it's used as a cutting tool to cut other materials. So it's used in drilling or used by as a drill. However, one of the things to talk about here that in its structure is that because all the carbon-carbon covalent bonds are used up, so there's 4 carbon atoms. Each carbon atom is bonded to 4 other carbon atoms. That means that there's no delocalized electron, right? And therefore it doesn't conduct electricity. Because there's no delocalized electron in diamond structure, therefore it can't carry a charge. As I said before, the movement of charge is, I think I said it before, but what electricity is the flowing or the movement of charge down a potential difference, or the gradient, which is potential difference. If there's no electrons that are out there to be released, then therefore there's no free flowing electrons, because delocalization is a flow of electrons. But if there's no delocalized electrons, no free electrons, you can't have electricity because they're not free flowing. They can't move. They're fixed in place in those bonds. They're in between those carbon. They're fixed in place, right, between these carbon covalent bonds. Right, high melting point. A lot of energy is needed to break the strong covalent bonds. Diamond is saturated and has covalent bonds. Diamond is saturated and has lots of covalent bonds. Therefore, the high energy is required to break all the bonds by obviously heating. One of the things that everyone knows about the high melting point, doesn't conduct electricity, hard covalent bonds, but normally people talk about this thermal conductivity, right? And diamond has a very rigid structure, so meaning the vibrations can easily carry heat throughout the structure. Diamond is an excellent thermal conductor, so it's good at maintaining and keeping that heat, right? Remember, solids are the best state of matter for carrying heat, because they vibrate, and because they're so close. And ones, especially the most dense or most rigid solids, are the ones that they're more tightly packed together, and they vibrate, and they can continuously vibrate because they're so close to one another. And with diamond, because the structure is it's such a rigid and such a rigid structure where all the carbons are arranged in this particular way, and they're kind of fixed in place, and they're so close to one another, I should say. Because remember, one carbon atom is bonded to four other carbon atoms. They're able to vibrate. What the vibrations can be felt throughout the entire structure, and therefore able to maintain that heat for a long time. So it's a very good thermal conductor. Next one, the next allotrope I'm going to talk about is graphite. So graphite is an allotrope, it's before such a form of carbon, and it has the following properties. So it has a covalent bond. So each carbon atom in graphite is bonded to 3 other carbon atoms by strong covalent bonds, creating a giant covalent structure. When you have, if that's the main thing, right? They always talk about what's the difference between. You can get a 6-mark question where they just ask you, the differences between the. I won't say 6-marker, but it could be an evaluate question when they want you to compare diamond and graphite, because those are the two what they usually want you to compare. One, and then that's just 1 mark. 1 mark is just saying diamond, each carbon atom is bonded to 4 other carbon atoms. In the graphite, 1 carbon atom is bonded to 3 other carbon atoms by a strong covalent bond. So that means they have 1 electron that's spare, 1 delocalized electron, but you still have a giant covalent structure that's being formed. Sorry, I can't really speak that well. I've still got my retainers in, but I'll try for the video. So you've got strong covalent bonds, and due to strong covalent bonds within each lattice of graphite, there's a high melting point, and it's still insoluble in solvents. Diamond is also insoluble in solvents. Alright, it's soft. One of the other things is that it's soft. So the carbon atoms form a layer of hexagonal 6-sided rings. Alright, so you can see the hexagonal rings where each carbon atom forms a bond with 3 other carbon atoms. So what if you say this one here, right? 1, 2, and be a 3, or be a third one there, really. I say not 3. That'll be that's the van der Waals intermolecular forces. 1, 2, and a 3. Like this one here, right? 1, 2, and a 3, and it's the same principle. They just had to show here, but this is they're showing it at an angle here, but realistically, this is a 2D sheet. If you was to look at it dead on at the same plane, it's a straight line. It's a sheet, and it can be described as 2D. And it's a regular lattice. It's one of the most regular lattices, or the most regular lattice that you'll see in chemistry, because it's a fine sheet, weak van der Waals molecular forces that they're regularly stacked upon one another. It's like paper in a way, in terms of the way that they're stacked upon one another. But yeah, that's it. It's soft. So carbon atoms form layers with hexagonal 6 rings, with each layer held together by weak intermolecular forces. So these weak intermolecular forces are called van der Waals intermolecular forces. These forces here, van der Waals intermolecular forces. And you can see here the electrons are, obviously you can't really see here, but ideally the electron, actually no, I'll go through it when I get to it. I'm getting a bit ahead of myself. I'll go through it. So because the layers can slide over one another so easily, right? Graphite is a very soft compound when you touch it, because if you was to touch it, that's how little energy is required to break these van der Waals molecular forces. You're actually breaking off, and some of that compound is just staying on your finger if you was to just to touch it, because it's that soft. And this makes it very useful as a lubricant and as pencil lead. All right, so to summarize, with graphite structure is the cause of all its properties. Its structure is the cause of all of its properties, and the structure of, I should say graphite, not graphite, forms layers of 2D lattices, and lattices are hexagonal. Each carbon atom has 3 bonds with 1 delocalized electron. And you might get for a 6-mark question, right? Where I ask, that's just 1 point there. That's just one thing you can say that's different about diamond, right? It has diamond has 4 bonds, diamond has with each carbon atom forms each carbon atom is bonded to 4 other carbon atoms, whereas with graphite, each carbon atom is bonded to 3 other carbon atoms with 1 delocalized electron, right? And when we're talking about the delocalization, which is what I was trying to get onto, is that graphite is different from other allotropes, right? Instead of having 4 bonds, it has 3, meaning that there's an extra electron in each carbon atom that's not used. This becomes delocalized and moves between the lattices. So you don't actually have to melt it. You have to do that at all. It's the delocalized electrons that are present because each carbon atom is only forming 3 bonds with other carbon atoms. That one delocalized electron is free flowing throughout the entire structure, and usually move between they move between the bonds they usually find where these van der Waals forces are here. That's where the delocalized electrons are present. They're free flowing between the lattices. They're usually found within this region. Actually, I don't want to use white. They're free flowing within these regions. And because of that, because they're delocalized electrons, they're free moving electrons, they're able to conduct electricity. What is actually conducting electricity is the free moving of charges down a potential difference. So, or across using via potential difference from a negative end to a positive end. If I'm wrong, I'm sorry, my physics teachers, I waste your time. But you get what I'm trying to say. It's down that potential difference, right? And that's what electrons, when they're free to move, you don't have to know this part, but the point of understanding what electricity is the free, why delocalization is so important is because you need to have free moving electrons in order to conduct electricity. They need to be free to move. If they're rigid, you might have electrons here, but if they're fixed in structure, you can't conduct electricity because they're not able to move. They're not able to move from one side of the wire to the other side. If you're using it as that example, they're not able to move from one side of the compound to the other. They're fixed in place, so they wouldn't be able to conduct electricity. Right? There's electrons here, with carbon obviously, but they're not free flowing. They're not able to move, so you wouldn't say they conduct electricity. So that's just what I'm trying to say. I know I'm speaking a lot, but just trying to emphasize the point so you just get what I'm trying to say. Or you could just move on you can just skip to different parts of the video, I guess. I don't know. Do what you want. Bonding between lattices, right? So the intramolecular forces are within the lattice, which is intra, which means within the molecule. Intramolecular, within the molecule. In the molecule, say, or inside the molecule. And these are the bonds that are held within the lattice, and the carbons are held together by strong covalent bonds, right? So the intramolecular is between the compound. We usually talk about, when we talk about intramolecular bonds, so here's the intramolecular bonds here, the carbon and carbon covalent bonds. So these the intramolecular bonds are the ones that are within the lattice or within the molecule, and those the strong carbon covalent bonds. And when we're talking about intramolecular forces, we're talking about the chemical properties usually. They're usually talking about the chemical properties. You're not usually talking about the physical properties. The physical properties are to do with the intermolecular forces, which are going down here. The intermolecular forces are between the lattices, and the graphite sheets or the graphite lattices are held together by weak intermolecular van der Waals forces. So these weak kind of electrostatic forces of attraction. So that's why covalent compounds have some ionic characters, and this is kind of a weak point charge in a way. So not all covalent compounds are completely covalent. Not all ionic compounds are completely ionic. They have some covalent character or some ionic character that gives them a bit of strength, and that's an answer that you give for year 2, and you'll see why when you do year 2. But anyway, when you're talking about the intermolecular forces, these weak van der Waals intermolecular forces, they determine the physical properties. So in terms of the state of matter, when you require a lot of energy to break these carbon covalent bonds. So you're always gonna first break those intermolecular forces first, and that goes from from a solid to a liquid to a gas, and then once you use immense heat in the gas phase, that's what breaks these covalent bonds, so the intramolecular bonds. So the chemical properties are decided by this, by the intramolecular bonds, and the physical properties are determined by the intermolecular bonds. I know I'm saying that many times, but just to make it clear what it is now. Right. And lubricant properties, right? So as intermolecular forces are weak, the layers slide over each other quite easily, and the sliding is used in lubricants and is also used in pencils, because as pencils move across the paper, lattices, for example, which are also known as the layers. So as pencil moves across the paper, layers of graphite rub off, right? So I said before that it's a soft structure. If you actually touch the graphite, these intermolecular forces are so weak that if you touched it, that's enough energy just to break off a lattice and it would stick to your finger, right? And that's what's happening actually with we can use that theory. The fact that they slide over enough, we can use that theory with paper. That's what it makes them. So that's what this is graphite here in my pencil this is a mechanical pencil, but you get it. But this part here is graphite, and when I'm going across the paper here, I'm actually breaking each lattice off. Each lattice is breaking off from the last lattice, and is going and it's now stuck to the paper. That is a lattice of this pencil here that's being brought onto the paper. That's just what's happening there. Because I'm just every time I'm moving across the paper, I'm just breaking off another lattice, breaking off another lattice, and those lattices just remain on the paper, and they allow us to draw whatever we want with a pencil. So that's what they're useful for. Or they could just be used as a lubricant. Alright, so the next part of the video is to do with metallic bonding. Metals and metallic bonding. So metals bond in different ways to non-metals. So the part I'm going to talk about now is the sea of delocalized electrons. So in a metal, the valence electron, and the valence electron is the electron on the outer shell. So the valence electron, let me say it again. In a metal, the valence electron, which is just a fancy way of just saying the electron that's on the outer shell, and the valence shell is just the outermost shell. So that electron, the valence electron, is just the electron that gets involved in bond forming, involved in the chemical reaction, involved in the bond forming, i.e., it's the electron that gets donated for ionic bonding. So if you're, for example, in Na, if you're doing NaCl, if you're forming NaCl, the valence electron would be that electron that's getting donated from the sodium valence from sodium's valence shell. That valence electron would be the one that's getting donated from the valence shell on sodium to the chloride atom, or it's the electron that gets involved for covalent bonding, the electron that gets shared on the valence shell or the outermost shell. That's just what a valence electron is. But in case you didn't know what it was, in case you see it, right? So in a metal, the valence electron, which is that would delocalize, and so in this case, the valence electron is free to move. It can just leave the structure and it can just delocalize and can move around the entire material. And this is referred to as a sea of delocalized electrons. So as you remember from GCSE, you should remember this from GCSE, but you'd form a sea of delocalized electrons. Oh, don't know what on earth has just happened there. I just wanted to have a little box. No. Pig. Alright, but actually I can just draw it here. What am I talking about? Yeah, I can just do it here. This is a terrible square, but you know, you have your ion core, your positive ion cores, and you have your valence electron that's being able to, you know, from each atom. These should be much more close towards one another. I don't know why I did it like that. I don't know why I drew them so far away from one another. it is a solid anyway, so it shouldn't be so far away from one another. And then but see, these electrons can freely move throughout the entire structure. You get the idea. They can freely move throughout the entire structure, these electrons. And the more the depending on the group, that will determine how many electrons are able to be released. So how many valence electrons are released, and how attracted they are. Because a group 2 would have a 2+ positive charge, so they're more attracted to the electrons are more attracted to the nucleus compared to a 1+ charge in for example in sodium. So this is referred to as a sea of delocalized electrons. Those electrons I showed before are a sea of delocalized electrons. Metallic bonding is viewed as a sea of free electrons surrounding a positive ion core. The positive ion cores are attracted to the free electrons, and this attraction between the electrons and the positively charged nucleus is an electrostatic attraction. Right. So electrical conductivity, right? So what I've talked about so far of metallic bonding is, if I was to separate it out, lattice of positive ions. Shouldn't be moving that too much. A lattice of positive ions. Ooh. And free electrons. That's it. That's literally it with metallic bonding. A lattice of positive ions, positive ion cores, you could call them, and then free or delocalized electrons, you say. Delocalized electrons. So metals are good electrical conductors, as a delocalized electron can move and carry a current. Also, so a general term for moving particles which carry current is called a charge carrier. So because they're able to carry that charge throughout the entire structure, or they can move the charge across from one side of the metal to the other side of the metal, which is what wires do all the time. They're just carrying, what wires do, right? They're just carrying a charge from one side of the wire to, it's a flow of electrons, right? And the electrons are the ones that carry the charge in coulombs. That's a bit of physics, but the electrons are the ones that carrying a charge, and they're constantly moving this charge, right? These charge carriers are moving because they're free flowing, they're moving these electrons from one side, they're moving this charge from one side of the metal to the other side of the metal down a potential difference, or down a potential difference, and that potential difference is defined by the voltage, right? And that's what metals are so good at. That's why we use them in wires, because they're just so good. The way that it's structured, the way it's structurally comprised, it makes it good for carrying that charge for electricity. Melting point. So melting point of a metal is related to its group. So group 2 metal will donate 2 electrons to the sea of delocalized electrons, meaning positive ion cores carry a 2+ charge, meaning the melting point is higher. So the higher the group means that you have more electrons that are donated to the sea of delocalized electrons, which means there's more electrons that are donated to the sea of delocalized electrons, but also there's an increase in charge. The nucleus that the electrons are being attracted to it's more positively charged, so there's a stronger electrostatic attraction. So that's 2 things you need to keep in mind. So group 3 metals would have the highest melting point compared for in terms of metallic bonding, right? Because they donate the most amount of electrons in it. They donate free valence electrons, and the electrons are attracted to a more positively charged 3+ nucleus of the ion. So free electrons are released per atom, right? Well, per ion, we should say, and they're attracted to a 3+ positively charged nucleus. So there's a very strong electrostatic attraction between the in a 3+ metals in 3+ metals from group 3. For example, aluminium's melting point. If it was to do period 3, I believe it is period 3. In period 3, between the metals of sodium, magnesium, and aluminium, aluminium has the highest melting point compared to sodium, magnesium, aluminium, because aluminium has property that I just said here before. Its melting point is 660 degrees. For example, compared to sodium, which has 98. You can see here, sodium which is in group 1, 98 degrees Celsius. That's its melting point. Magnesium, which melts at 650 degrees Celsius because it's in group 2, and then going to group 3. 660 degrees Celsius. So as you can clearly see here, there's a trend between each group. That's it for the video. Hopefully it helped.